Dear listeners, welcome all of you who are interested in electroencephalography, EEG, and event-related potentials, ERP techniques, and all of you who are interested in collecting, annotating, standardizing, storing, processing, sharing, and publishing data from electrical activity of the human brain. Welcome to the fourth part of our video tutorial that practically provides you with the procedure of EEG and ERP data and metadata collection. For those of you who are beginners, we recommend first listening to the previous parts of our tutorial. In the first part of our tutorial, we introduce the whole EEG data lifecycle that you can see in the picture. It describes the phases through which the EEG or event-related data pass during their life. In this part, we will focus on the data collection phase, marked green in the picture. That is preceded by the phases of experiment planning, experiment design, and experiment approval. While the experiment planning and the process of creating an experiment prototype were in more detail presented in the second part of our tutorial, data security and legislation issues, together with the experiment approval phase, were introduced in the third part of the tutorial. The data collection phase includes all procedures from setting up the hardware and software infrastructure and familiarizing participants with the experiment design to getting all needed EEG data and metadata. You can see the outline of the fourth part of the tutorial dedicated to EEG and ERP data and metadata collection procedure. At first, each participant is informed about the goal of the experiment, course of the experiment, used equipment, behavioral rules, etc., and signs the informed consent. Then, they are asked to provide metadata that are needed to evaluate and interpret the experiment later. Then the hardware and software infrastructure that was already introduced in the second part of our tutorial has to be set up for a specific experiment. Before the procedure of data collection itself starts, the participant has to be technically prepared for the measurement. During and just after the experiment, the collected data are continually evaluated and the participant is eventually asked to change his or her behavior related to the experiment. At the end of the experimental session, the participant is asked for a feedback. Eventually, another set of metadata related to the performed experiment is collected. The BCI project BASIL is presented on the examples where it is suitable and not only at the end as it was usual in the previous parts. This part is also concluded with a short quiz. Prior to measurements, all participants are familiarized with the goal of the experiment, overall experiment procedure, used equipment, environment, conditions for participation in the project, and related legal conditions, including data security. This is given to them in a written form that is accompanied by a verbal commentary. They can, of course, ask additional questions. If they understand and agree to all conditions, they sign the informed consent, which is stored and archived in the neuroinformatics laboratory. In case of ERP experiments, there is one extra issue that has to be taken into account. Since the stimulation often requires some kind of flashing, for example, symbols on the screen or LED diodes, the participants are questioned whether they suffer from epilepsy. In case of capturing a large variety of biodata and using more sensing techniques, the participant has to agree with each type of data capturing explicitly. After signing informed consent, the participant is asked to provide metadata that are necessary for the interpretation of the captured data. Eventually, provide metadata for contacting him or her again if any repetition of the experiment is considered. In any case, the minimum set of metadata is always collected. The basic metadata set usually includes name and surname of the participant, his or her sex, age, and laterality. However, other types of specific metadata could be collected. For example, possession of a driving license and overall driving experience in case of experiments focused on attention of drivers during simulated drive, or a questionnaire concerning the state of physical and mental health and life habits when the experiment focused on the correlation of heterogeneous biodata is performed. Personal metadata such as an email address are collected only in the case we need to contact the participant again, typically if the experiment is repeated at some time span. The metadata are collected manually or electronically. An electronic form is preferred since it is easier to ensure the secure storage of data immediately. When the metadata are collected manually outside the lab, special rules have to be applied to ensure their security. Although the basic hardware and software infrastructure for performing EEG and ERP experiments is prepared in advance, we discussed this infrastructure already in the second part of our tutorial, it is necessary to set some of its components for each type of experiment. This applies in particular to recording and then for stimulation that is performed during ERP experiments. For stimulation, software tools or hardware devices could be used. Setting up both stimulation and recording software will be described in more detail on the next slides. An important step is to check synchronization of EEG signal and stimulation markers, since this is an essential functionality for ERP experiments, and from time to time it does not work correctly on the first attempt for various reasons. A very practical thing is to prefer the battery operation of the amplifier whenever it is possible, since the electrical interference is substantially eliminated. However, it means not to forget to charge the batteries in advance and take them with. Of course, if we are outside the laboratory and thus use the mobile EEG equipment, all the components of the infrastructure have to be interconnected. The setting of the stimulation depends on the fact if a hardware or software stimulator is used. Software stimulators have usually wider use, but creating more complex protocols can be redeemed by the need to write a piece of source code. Now we can take a short look on examples of stimulation protocols created in the program OpenSesame, shown on the left, and commercial software presentation that is shown on the right. The stimulation protocols have been created for the BCI project BASIL. The project BASIL was introduced already in the first part of our tutorial. And these two software tools were used just to compare the usability and user-friendliness of them. The stimulation protocol in OpenSesame has been in fact developed using its visual interface. Here the generated code is presented and compared to the source code of the presentation software. Here the protocol was really coded. The stimulation protocol that is presented to the participant was also already described in the second part of the tutorial. Here in the middle of the picture, you can see one of 6 presentation modes of the matrix of 9 symbols. Each symbol represents an activity or requirement the user of the BCI project BASIL needs to perform. During the stimulation process, always one row or one column flashes in a random order. In the code, you can see that each stimulus is tied up to a specific part. Finally, a random order of stimuli presentation is ensured by putting them in a loop.
Now I would like to quickly guide you through a process of editing a workspace in the Brain Vision Recorder. Click on File, Edit Workspace. Here we can set up the raw file folder to which the data are stored by default, and automatic file name generation that corresponds to the names of files as they are automatically created, but both can be changed at the time of initiating an experiment. Click Next. Here we can scan for amplifiers. Then we can see that we have 5 EEG channels with the following names and their corresponding physical locations on the amplifier. The sampling rate is 1 kHz, which is commonly enough for ERP experiments. And here is some basic filter settings. Let's move on. Raw data saving filters are used even before the data are stored to the drive. Therefore, we want to keep the signal as undamaged by filtering as possible. 0.1 and 250 is one of the choices that keep the signal white, unfiltered. Segmentation filters are used as the signal is averaged into epochs. 0.1 and this time 440 Hz as high cutoff filter can be used as we want to get rid of higher frequencies, especially electrical noise at 50 Hz. The same goes for the display filters. Here we want to keep the signal filtered in the online displaying of it. Let's move on. Here we can see the groups of stimuli as they are averaged to individual trials. Therefore, we can see how they differ for each conditions and, for example, find the P300 at any of them. Each group can correspond to one or more stimuli. In this case, we decided to use just one stimulus for each row and column. Here we can see our epoch extraction settings. We decided to use 100 before as the starting point and 1 second after the stimulus as the end point. Now we can even set our artifact rejection, but in our case it's disabled. Finally, we can confirm, save and overwrite.
Now we are in the situation the participant has signed the informed consent, provided us with necessary metadata, and the whole hardware and software infrastructure has been set up. Before starting the experiment itself, the participant has to be technically prepared for EEG signals measurement and needs to know some basic behavioral rules. You can see the preparation of the participant for EEG data capture on the video. First, an experimenter applies an abrasive gel on the participant's forehead and earlobe to ensure better adhesion and conductivity of reference and ground electrodes. In this case, the reference electrode is placed above the bridge of the participant's nose. Placement of the ground electrode on the ear is a standard procedure. The ground electrode is usually equipped with a clip, but as you can see, it is also fine to use a common patch. To monitor eye movements of the participant, a potential that exists between the front and the back of the human eye is measured. You can see that so-called electroencephalography electrode, in short the EEG electrode, is placed near the participant's eye. The signal obtained from this electrode is very useful when we need to detect eye movement artifacts. All electrodes, it means reference, ground, and EEG electrodes, are applied using a conductive electrode paste. The participant is given the standard EEG cap of the size of his or her head that uses the international 10 to 20 system of electrode placement. In fact, 19 electrodes are used, but for many ERP experiments having 3 to 5 active electrodes is enough. A conductive gel is applied to the electrodes in the EEG cap to increase conductivity. It means that so-called wet or gel electrodes are used, in this case, although dry electrodes are also widely tested. When the EEG cap is successfully placed, the participant is taken to a soundproof and electrically shielded cabin where reference, ground, and EEG electrodes as well as the EEG cap are connected to the amplifier. The impedances of all electrodes are checked and corrected if it is necessary. To ensure obtaining high-quality EEG data, the impedance of electrodes should be kept below 5 kΩ, but sometimes we are more strict and 2 kΩ limit is applied. Then the participant is familiarized with basic behavioral rules, asked to sit comfortably, pay attention to the stimulation, not to move, and limit his or her eye blinking. Then the experimenter shortly repeats the goal of the experiment and provides other guidance related to the expected brain activities. To increase alertness during ERP experiments, the participants are, for example, instructed to silently count the total number of target stimuli presented on the monitor. When the participant assures experimenters that he or she understands all the circumstances of the experiment, the soundproof cabin is closed and the experiment is launched. In case of ERP experiments, the stimulation starts and the recording software is run to store the EEG data together with the event markers. Here on the slide, you can see the screenshot from the Brain Vision recording software that shows in colors the impedances of 5 connected electrodes labeled as FP1, FP2, FZ, CZ, and PZ, and the impedances of the reference and ground electrode. While the impedances of most electrodes are kept up to 2 kΩ, the impedance of the frontal electrode FZ attacks the recommended 5 kΩ limit. The ranges of displayed impedances can be set up in the right window. Now we are starting the stimulation using a protocol for the BCI project BASIL that you have already seen. The participant focuses on one of 9 stimuli within metrics representing his or her possible activities and needs. For example, to open a door, switch on the light, listen to the radio, or go to the toilet. It means he or she focuses on the row or column containing the selected symbol when this row or column is highlighted. These 6 stimuli, 3 rows and 3 columns, are flashing in a random order as you can see. The participant who is, for example, hungry, focuses and pays attention to the first row and the second column. Focusing attention on one flashing row and one flashing column elicits the P300 component, and the intersection of the row and the column represent the required activity or need. The rows and columns flash until we are able to detect the symbol the participant focuses on. In the next video, we will see how the EEG signal together with event markers are recorded and how the occurrence of the P300 component in the average signal is evaluated.
Let us now start the recording. To do it, click on the green arrow. Now we have to type the file name and confirm. At this point of time, continuous EEG is transformed into event-related potentials according to the stimuli markers. Each stimulus corresponds to one row or column, and we want to confirm the target stimulus by observing the P300 component at one row and one column. Because event-related potentials are enhanced by averaging, we have to wait a few moments until they are more prominent. So far, there is no significant positive peak. Maybe here we have to wait a little bit longer until we can see it. So there seems to be a sign of the P300 component at the row 1 average. At the PZ electrode, there is a peak around 400 milliseconds, mainly prominent at the PZ electrode, less on the CZ, and even less on the FZ. There is no such effect on the row 2 average or even row 1 average. To find the column, we have to look at column 1, column 2, and column 3. Column 1 has been distorted by blinking. That's why it may be useful to set up the artifact filters. And there is some sign of the P300 component on the column 2 average. So far, the column 2 looks the best, and we need to wait a little bit more until we can confirm the second column. Meanwhile, let's have a look at the row 1. And there still is the P300 component partially overwritten by the blinking artifact. Nothing at row 2, nothing at row 3. Yes, so at this point I believe we can call it the column 2. So by finding the P300 component at the row 1 average and the column 2 average, we can say that our target stimulus was the foot.
At the end of the experimental session, the participant is asked to give feedback, eventually to provide another set of metadata related to the performed experiment. The feedback is important, especially during the first experiments, to possibly modify the experiment design if it turns out to be difficult to cope with. Additional metadata may not necessarily be provided by a participant. It may also be recorded by the experimenter. These kinds of metadata could, for example, describe any non-standard behavior of the participant or the infrastructure during the experiment that can influence the interpretation of experiment results. The last step is also very important for participants. They are provided with head cleaners. Before we finally store the collected EEG and ERP data and metadata, it is necessary to evaluate them. To ensure that the data recorded are of sufficient quality, there are multiple steps to follow. First, before you even start, it is good to follow common recommendations, such as in Log 2005, to minimize disruptions to our experiment and deliver as clean data as possible. Although some signal processing techniques can partly eliminate undesired noise, they will always damage the signal of interest to some extent. So there is really no replacement for clean data. After the experiment, several procedures can be performed to check the quality of obtained data sets. For example, presence of artifacts can be evaluated. Moreover, you should check if the results of an experiment are consistent with your aims. For example, if the P300 experiment was performed, the P300 component associated with target markers can be expected. If it is not, you can ask, is this just an individual variability or some mistake in the design? During the BCI project BASIL, we perform BCI experiments not only in our lab, but mainly in hospitals and in the home environment of patients. Although the experiment design is the same and modifiable as it is in lab conditions, we have to cope with several difficulties based on the variability of the patient environment and their current state of health. Of course, outside the neuroinformatics laboratory, we have to unpack the whole infrastructure, deploy it in a small space at some hospital units, respect the patient's current state, the operation of the hospital unit, and cope, for example, with various light conditions. On one hand, it causes difficulties with the design and testing of the BCI system. On the other hand, it makes the system robust and usable under different conditions. On the slide, you can see the picture from the experiment performed in a hospital. Here, 7 electrodes and a classic matrix experiment design were used. With the hospital testing of the BCI project BASIL, we are approaching the end of this part of our tutorial. Now we have time for a short quiz. More than one answer can be correct. Why do we need the informed consent? A. It is a recommended bureaucratic step. B. It is the easiest way to obtain personal information from participants. C. We know that the participant understands all the circumstances associated with her or his participation in the experiment and agree with them. The right answer is C. When collecting metadata from the participant, it is important: A. To get only the minimum set of metadata important for interpretation of experiment results. B. To get as much personal data as possible. C. To draw up a lifestyle questionnaire. The right answer is A. Which of the following parameters are usually set up in the recording software before the experiment starts? A. Sampling rate. B. Cutoff frequencies. C. Age of the participant. D. File folders for storing data. The right answers are A, B, and D. Why is it important to check the impedance of EEG electrodes before the experiment starts? A. To improve safety of the participant. B. To get high-quality EEG data. C. To ensure equal conditions for each experiment. The right answers are B and C. What is the reason to use the EOG electrode? A. To detect eye movement artifacts. B. To get another reference voltage. C. To check impedances of other electrodes easily. The right answer is A. Our quiz is over, and now we can take a short look on our references. We would like to invite you to the 5th part of our tutorial, where we will talk about annotation, storage, sharing, and publication of EEG data.